Everyone has been working hard on the homework and having a wonderful experience, and it's been stimulating and enlightening. Yep. Good. Good. Oh, good. Well, you should give Danny all the credit because he put it together. Okay, good. Any questions about the homework before we start in?
I kept getting stuck on the time integration because I kept eliminating time as a variable, and I didn't know what I was doing.
Okay, have you ever done a time simulation before in your previous life? Not really?
Not really.
Okay. The thing you need to do is go to MATLAB and follow directions. But let me tell you what the basic idea is. If I've got a differential equation of any sort, well, let's look at this one. Well, you can put a damping term in just to add interest. Okay, and these QNs are functions of time, and they come from taking the displacement of a point on your wing and writing it as a modal series, right?
Mm-hmm.
So eventually you need to have a representation for that, which you'll get from that piston theory. And then, so you end up with an equation that looks like this. A time integration is numerical time integration. Of course, you would try to solve this equation analytically in time, but I didn't ask you to do that. You could actually have done that in this case, but that's not what I asked you to do. If you want to solve this equation numerically, first of all, there's all kinds of software, because this is done all the time in all fields of engineering. And what the software does is following. It says Qn at some, at some short time delta t, where that's a time step that in most cases you don't even have to pick. They'll select it for you, but sometimes you have to pick it yourself. And I'll tell you how to pick it in a moment. Is equal to Qn at time t equals 0 plus Qn dot at time t equals 0 times that time step delta t, okay, plus Qn double dot, yeah, thank you, at time t equals 0 times delta t squared over 2, actually over 2 factorial, but it's also a 2, and then is a delta t cubed, and some software includes delta t cubed and some doesn't. You need to have at least delta t squared and Qn double dot, and the idea is if you tell me the initial value, which you have to tell me, of Qn and Qn dot, then I can compute this one by solving this equation for Qn double dot. So I know this at time t equals 0, and I know this, and if you look at the right-hand side, it turns out in this case you'll know these two, okay? These terms also. Then you'll solve this equation for Qn double dot, and it'll produce Qn at small time later. And then, once you know everything that's happening at delta t, you do the same thing, and over here these zeros get replaced by delta t, and this gets replaced by 2 delta t. If you had, that's what you do if you had to write the software yourself, but MATLAB has already done all that for you. But that's what MATLAB is doing, more or less.
Okay.
Okay, so what you need with MATLAB is you need to take this differential equation, expressing this in terms of these small q's, give it to MATLAB and say, here's my differential equation, and here are my initial conditions at time t equals 0. Please plot out the time history for me, and MATLAB will do that. Okay? Does that help?
Yeah.
Okay. Okay. And this is a very common thing. I mean, any field of engineering or science, you can think of someone's doing time simulations at various points in their career.
There are good examples on that website if you look up ODE45.
Yeah.
Yeah, I wish I had thought to do that. Thought I had to make the code myself.
Yeah. Okay. So if you want to do that, even though it's due today, go ahead and do it. And I'll still look at it, okay? And catch me on a good day, I might give you full credit, or it might, take off a half a point or something, depending on how it's feeling. Okay. It'll be a good learning experience for you. Any other questions about homework? Hearing none. You can still ask questions later. Hearing none, I'm going to go right on ahead and talk about 3D supersonic flow. We introduced that last time, remember? And I went through it very quickly, and I'm sure you understand everything I said and filled in all the gaps. But just in case, there are some lingering questions. I'm going to go back and revisit that a bit. Okay, I'll call it page 1. So page 2. How many people listened to Paul Harvey on radio? That was probably before everyone's time. He was a newscaster, had a very resonant voice, and he was, I think he was either a newspaper person or would like to pretend he was, because that was a higher form of church at one time. Newspaper people ranked above radio and TV people at one time. Think about that, because now they get paid diddly, and the TV people are getting paid two amounts of money. But anyway, he was talking about, in his radio broadcast, he was saying, page 1, and that would be the headlines, right? And now moving on to page 2. You had to be there to appreciate it. Anyway, okay, 3D, supersonic flow. So we have our equation, our beloved equation. Oh, sorry about that. Here it is. The Laplacian of the velocity potential minus 1 over the speed of sound squared times the substantial time derivative, which includes the convection term, d dt plus u infinity d dx, operating twice on the velocity potential equals 0, right? And in 2D flow, we just drop this term. Remember that? Well, we can't do this in 3D flow, right, by definition. So we're still going to do what we did before in 2D flow. What I mean by that is we're going to take phi, which now depends on x, y, z, and t, and assume it's some function which we hope to determine, x, y, and z, times e I omega t. Okay, we're going to assume simple harmonic motion in time, recognizing that we can always, in principle, it may be difficult in practice, but in principle, construct solutions for any arbitrary time dependence once we know the solution for harmonic motion. We're going to do that. And just as before, we're going to take, in 2D flow, we're going to take the Laplace transform of phi bar, all right? And that will produce something we'll call capital phi, which now depends on what? It depends on the Laplace transform variable p, never to be confused with pressure, as well as y and z. And of course, it also depends on omega, right? So we're taking this, put in here, and all the time derivatives get replaced by I omega. We take this and put it in here, and all the x derivatives get replaced by p, right? So then what that will do is it gives us the following. We'll have second partial of capital phi is respect to y, plus second partial of capital phi with respect to z, equals mu squared times capital phi. Where this mu squared is the same mu squared we had before in 2D flow, right? Because we did the same thing we did with 2D flow, and so it involves Mach number and speed of sound and frequency. I won't bother to write that down. Okay, but whereas before, when we could drop this term, we had an ordinary differential equation, second order constant coefficients, and we went on our merry way. Now we have to do something. We have to do something with this. And I propose that we take a Fourier transform rather than a Laplace transform, mainly because the Laplace transform will give you the wrong answer. And Kevin rightly said, well, why? After all, there's symmetry, and so if either the solution is either symmetric, I can always take a solution, any solution with respect to y, and divide it into a symmetric part and an asymmetric part. And And therefore, if I know the solution one half of the domain, I know the solution the other half. That's true, but I can't get around the physical characteristic that something is happening for y less than 0 and something else is happening for y greater than 0, and there's no way I can get around that. I can't, to use the Laplace transform with respect to y, I would have to have the flow undisturbed either for y less than or greater than 0. Could be either way. I could reverse my direction, right? But if it's just rather symmetric or asymmetric or whatever, as long as it's disturbed throughout y, I'm stuck as far as using Laplace. So I have to use Fourier. Okay, so now, with that said, we're now going to take the Fourier transform. Oops. Got excited there. We're going to take the Fourier transform of capital Phi with respect to y, and I'm going to call that Phi star, which is what I called in the book. That's why I could call something else. And what do I mean by Phi star? Phi star, by definition, is the integral from minus infinity to plus infinity of capital Phi, which depends on P, Y, and Z, and of course on omega, e to the minus I gamma y dy, where gamma is the Fourier transform variable. Often in the literature you'll see alpha, but I kind of like to use that for angle of attack. Now I could use alpha and then tell you never confuse it with angle of attack, but here I'm giving you a break and calling it something else. Okay. So what does that do? Well, what that does is every time I see a derivative with respect to y, it gets replaced by I gamma, right? Because again, just to remind you, if I wanted to compute, if I want to take the Fourier transform of this, well, let's do this term since that's actually I'm violating my rule of doing the simplest term here, and you do the more complicated term. If I take the Fourier transform of this, it's just the Fourier transform of this. If I take the Fourier transform of this with respect to y, it's just a second derivative of the Fourier transform with respect to y with respect to z, right? But here, I want to replace the Fourier transform of the second derivative with respect to y in terms of the Fourier transform itself. And so I have to do the following. I have the Fourier transform of this, by definition, is the integral from minus infinity to plus infinity of this right? Right. And now if I integrate this by parts twice and assume that things die off at y equals plus and minus infinity, so the tail terms go away, each time I integrate by parts, I reduce this from the second derivative to the first derivative and then on to the function itself, and I get an I gamma each time because it's minus I gamma, right? But then there's a minus sign because of the integration by parts, so it turns out to be plus I gamma. So this turns out to be I gamma squared, the integral from minus infinity plus infinity of phi e to the minus I gamma y dy, which is by definition phi star, right? Okay, so what does that do? Well, all that does is I've now got phi star here, but times I gamma squared, otherwise known as minus gamma squared. And I take that on the right-hand side, right, and collect terms. And so now I have the following. I have an ordinary derivative of phi star with respect to z equals mu squared plus gamma squared times phi star. So this looks in transform space just like the equation I had before, right? More or less. Except now when I do the inverse, I have to invert the Laplace transform and also the Fourier transform, right? So if I want to go back to phi bar, which depends on x y, z, and of course parametrically it depends on omega. Right? It is the inverse of capital phi star e to the plus px e to the I gamma y dp d gamma, and the integral over gamma is minus plus infinity, but because I chose in a weak moment, well actually, it's a 1 over 2 pi here, and then because I use the Laplace transform with respect to x, is 1 over 2 pi I, and the integral from minus I infinity to plus I infinity. Okay. But what is phi star? No, we can compute that. Remember what we had? We had this. Well, phi star, naively, is a e to the plus mu squared plus gamma squared square rooted times z, it's a small z, of course, plus b e to the minus mu squared plus gamma squared 1/2 times z. Okay? Okay. But again, I'm going to naively throw that away because it blows up, apparently. Actually, it depends on Mach number and frequency and so forth. Sometimes these solutions, one of them blows up and one decay, and sometimes one's an outgoing wave and sometimes one's an ingoing wave. So I really had to be more careful than I'm sharing with you. But it's the same sort of calculation for 2D flow. So phi star is b e to the minus mu squared plus gamma squared square root times z. And then we apply the boundary condition. Remember what the boundary condition was? It's the same boundary condition we had before with a little twist, as you'll see. The boundary condition, remember, was d phi dz at z equals 0 equals a combination of terms which I called W sub A. But now I'm going to assume simple harmonic motion, which will give me bars on both sides. I'm going to take a Laplace transform with respect to x and a Fourier transform with respect to y for this equation too. So this will become d phi star dz equals capital W star, this is the double Fourier transform, Laplace transform, and also simple harmonic motion. So I use this boundary condition and this solution, and I can determine B, just as I did before, right? I won't go through the details of that. But basically, B will turn out to be minus capital W star over U squared plus gamma squared square root, which is the same thing we had in 2D flow, except the gamma wasn't there, right? And by the way, look at phi star. Phi star, if I'm content to have phi star z equals 0, it's just B, right? And for the moment, I'm going to be content to know the solution only on the wing, because that's where I want to know the pressure if I'm going to do flutter analysis or any other kind of analysis. So, then, phi star at z equals 0 is equal to minus W star over u squared plus gamma squared. Okay. Now all I have to do is invert that twice. And I gave you the formal inversion formula a moment ago, but you'll be thrilled to know that someone has already worked this out for you. Okay. And so phi bar, everything gets multiplied by ei omega t, right? Phi bar function x, y, and z. Because this is a product of a double transform of this and effectively a double transform of that, is a convolution integral. But it's a double convolution integral over spatial variables in both the x and y direction, which means we have to introduce two new dummy variables. So this is equal to minus sign. The double integral of w bar a, that depends on c and eta, the dummy variables. Then the Laplace inverse, the Fourier inverse of 1 over g squared plus gamma squared, square rooted. Sorry, I left myself with not quite enough room. dc 8 eta. Right? So the whole thing is, can I invert that? And you can. And the equation for it is in the book, and I wrote it down the other day. The key thing to know is the following. Whoops. There. The key thing to know is when you do this double inverse, oh, I don't can make the sign. When I do the double inverse of that, it's something. But in particular, it's only non-zero. Only non-zero when c, that's the flow direction variable, is greater than 0, because we're still in the supersonic flow. And if I pick the spatial flow variable to be 0 at the forwardmost point of the wing, right? Then this integral will be 0. This integral will be 0 when I'm in this region. And I'm also less than x because nothing behind the point of interest, because the supersonic flow can affect the point of interest. But now you see the essential challenge of 3D flow. Eta, fortunately, is 0 except when eta is equal to y plus, less than y plus x minus c over beta, and greater than y minus x minus c over beta. And beta is this magic factor, the Mach number squared minus 1 to the square root. By the way, in subsonic flow, the same factor will appear, except it will be 1 minus the Mach number squared, right? I mean, after all, in supersonic flow, this is a positive number, right? And subsonic flow, this is the imaginary number. So this solution can't possibly work that. Okay, so let me draw the picture again. Thank you. I'm going to draw a delta wing. I could draw other kinds of wing, but I'll draw a delta wing. And I want to know the solution at this point, which I'll call xy. Actually, I want to know the solution at all points xy on the wing, but let's pick a typical point. We can get the solution at one point, and presumably we can get the solution at other points as well, right? Okay. Of course, this is the x-axis, but it's also the c-axis. And this is the y-axis, but this is also the eta-axis, right? And I'm integrating over c eta. And I'm integrating because of the character of this inverse. I'm integrating between 0 for all c, between 0 and this value x, right? That's fair enough. But then I'm also integrating for all eta between here and here. And what is that? well, what are these limits? Well, they're lines, right? Because everything's linear in y, x, and c. They're just straight lines. And they have a certain slope, which is determined by the Mach number. Hence, they're called Mach lines. And what happens? When c actually reaches the x point, this term goes to 0, and the integral is over a point, right? Just y. But on the other hand, when c equals 0, when I'm up here, I integrate from y minus x, right, over beta, to y plus x, also over beta. And so I can draw the line using my limited artistic ability. I am going to cleverly choose the Mach number so that beta equals 1. All right? Choose beta equals 1. If beta equals 1, then Mach number squared better be 2. And if I take a square root, that's the square root of 2. So I'm looking at Mach number equals 1.414, right? Which is a nice supersine Mach number. If I do that, then what is the slope of this line? If eta and c have the same coefficient, well, it's 45 degrees, right? The tangent is 1. So I've cleverly made things so that, let's see if I can draw a 45-degree line. That's this line. That's eta equals y minus x minus c for beta equals 1. And then there's another 45-degree line up here. This is y plus x minus c, again for beta equals 1. So what does this mean? It means that to find the solution at this point, I need to integrate in this region, right? Well, there's a slight difficulty. I know this. This is the motion. This is describing the motion of the wing. I know that on the wing. I don't know it off the wing. I don't know it off the wing. So I cannot perform this integral unless I do some further thinking. So what we're going to do is we're going to discover that while we don't know this off the wing, we know something else, which will be just enough information to find the solution not only on the wing itself, but in all these other regions as well, off the wing. I don't need to find it everywhere, but I need to find it within these dotted lines. So when I do the solution, I need to find the solution on the wing, but also here in this area, and also down here in this area. Okay. But we're going to do that. And so this will motivate us now to think about what are the conditions that apply in the plane of the wing on z equals 0, but off the wing. But off the wing. I mean, we do know something, as it turns out. Okay. Now I've been going a certain rate of speed. I'm going to pause, gather my strength, and ask if you're still with me, more or less. You're still with me. Okay, fine. So let's now talk about the boundary conditions in the plane of the wing, but off the wing. Okay. All right. I submit to you that there are two things I know. I'm in the plane of the wing. By off the wing, there's some fluid there. I know two things. I know the pressure is continuous as I go through that surface. Yeah, that is the pressure at z equals 0 plus. Z equals 0 plus means z is 0, but it's ever so small the distance above, is equal to P equals z equals 0 minus This says the pressure is continuous as I pass through that surface where there's fluid but no wing. By the way, as we'll see in a moment, often the pressure is discontinuous from the top to the bottom of the wing. All right. In fact, if the pressure were not discontinuous, there wouldn't be net pressure and there wouldn't be force on the wing, right? Which would be, well, the Wright brothers would still be trying to figure out how to fly if that were true. So that's not true. But off the wing, I should probably say this is off the wing. That's true. Well, we know something else, and that is the phi dz, that's the fluid velocity component in the z direction. At z equals 0 plus is equal to the fluid velocity component at z equals 0 minus. That just says, you know, the flow velocity, the normal flow velocity is also continuous. By the way, d phi dx and d phi dy may not be. Why? Because we left out viscosity. And there can be discontinuities in those components. That's not normally stated in the textbook, but it doesn't really matter because we don't need them because, as you'll see, it doesn't really enter into the calculation. But there can be discontinuities in some of the other velocity components. If you leave out viscosity, of course, you put viscosity in, then everything's continuous. Right? Okay. Now, a little magic will be performed. No, not too much. We need to think of, now's the time to think about symmetry and antisymmetry. But we're going to think about symmetry and antisymmetry with respect to the z coordinate. Okay? So we're going to talk about symmetry and antisymmetry with respect to z. So remember I had this W sub A on the wing? Well, I actually have two WAs. I have one on the top surface and I have another one on the bottom surface. Well, think about it. Let's see. Well, let's look at this case. Here's a profile. I'm looking at the profile of the wing now. That's a pretty poor drawing. Wish I my artistic build. But let's pretend like that's symmetric, top and bottom, right? And W I'll call it Z equals 0 minus. Is that what I want to call it? Well, yeah. I don't use that notation. I'm going to put lower and upper. So L means lower. And that's this distance here. It's a function of X and Y, right? Obviously. Could be a function of time too, except we're going to assume harmonic motion. And this is W upper. And by the way, if I'm looking, I can look at the case where omega is 0 and there is no oscillation, right? And this is just the thickness of my wing, right? In fact, this is usually called the thickness problem. That's what aerodynamicists call it for historical reasons. But if I want to do the dynamic case, I think of these are two membranes. They're moving up and down symmetrically with respect to this. But now here's where the notation gets a little tricky. This is really down from Z equals 0, and this is really up, right? So in the notation, in the symmetry and antisymmetry discussion, W upper is equal to minus equal to minus W lower. Okay. If that's true, keep with me now. If that's true, then this WA, which involves time derivatives and X derivatives, but not Z derivatives, it also has the same characteristics. Remember what WA is? WA is what? Is dW dt plus U infinity dW dx. The point is that the time derivative and x derivative don't change the symmetry and asymmetry properties with respect to the z coordinate, right? So if this is true, then WA upper is also equal to minus WA lower, right? But what's this equal to? This is equal to, from the boundary condition on the wing, this is equal to phi dz, z equals 0 plus, and this is equal to d phi dz, z equals 0 minus, but with a minus sign, of course, with a minus sign because of this minus sign. So what I've shown is that on the wing, d phi dz is minus d phi dz. That is d phi dz 0 plus is equal to minus d phi dz 0 minus. And then, okay, are you with me? And then there's a time when I go to the trailing edge, I go to the leading edge, and there's a common point that's the interface between on the wing and off the wing. And I appeal to continuity, and I say, therefore, this must be true off the wing as well. But off the wing, I just told you a moment ago, this must be equal to plus that, right? Is that possible? I'm sorry? Yeah. Well, it's not stagnation point. But if I tell you, what I'm really saying is, I'll just use two arbitrary symbols. I'm saying A equals B, and I'm also telling you that A equals minus B, right? What values of A and B satisfy both equations? 0. So I have shown you, in this case, that d phi dz is 0 off the wing. That's fantastic. Why? Because if I know d phi d0 is something on the wing, and I know it's 0 off the wing, then when I do that integral, I know d phi dz everywhere, and life is beautiful. Okay? Life is beautiful. Yeah. There's only one little problem. For this case, I've talked about the pressure is clear from symmetry, and you can show it mathematically. The pressure on this surface meant to equal to the pressure on that surface, right? Well, there's no net pressure. So, you know, this is very nice, except it's not the problem I really want to solve. I want to solve the problem where I've got a wing which is deforming, right? And where this mean line is moving up and down, it's pitching or heaving. I really want to look at the other case where the upper and lower surfaces are anisymmetric, that is, which means basically that WU equals plus WL. Which turns out to give you a net pressure across the surface, which is the case of interest. This is so-called lifting case. Okay, so remember what we've shown here. This is fine, and if the upper and lower surfaces are both, you know, in phase and being away and doing all that thing, we can solve the problem without really treating the off-wing case, the off-wing region, because d phi dz is 0 there, and when we do the integral, we just set those off-wing contributions to the integral to 0, and we're done. We just really have to integrate over the surface of the wing itself. But unfortunately, that's not the case when we are interested in having a net pressure. Okay? So now let's look at another case. Are you still with me? Okay. Good. Now I'm going to look at another case. I'm going to look at a case where I have an infinitesimally thin surface, okay? And I'm going to put it at an angle of attack. So, very thin, wing. By the way, it's a linear problem, right? So I can take any arbitrary distribution and always of W sub A or deformation and always write it as a symmetric part and an asymmetric part. And the part we've just done is the easy part, and usually a part you don't bother with in aeroelasticity because it doesn't lead to any net forces. So here's what I'm saying is, if this thing really has an airfoil like this, that thickness within the framework of our linear model doesn't contribute to the net pressure across its wing. It's just as though it were an infinitesimally thin wing, right? By the way, this doesn't have to be a straight line. I can have curvature. Okay, so I could also do a case like this. But again, I would just ignore the thickness part and treat it as infinitesimally thin, but with curvature. Okay, that would give me a different W sub A than in this case, but in both cases they would have the same symmetry and asymmetry properties. Okay, well in this case, WA upper equals WA lower, right? I mean, how can it be different? It's infinitesimally thin, right? Okay, so that says d phi dz as z equals 0 plus equals d phi dz at z equals 0 minus on the wing, right? That's what it says. Well, I already told you a moment ago that that's true off the wing too, because there's continuity of the normal velocity component. So this is true on the wing. It's also true off the wing. It tells us absolutely nothing about what d phi dz is. It's not 0. I know that. It's not 0. Well, are we stuck? Well, not quite. Now I'm going to appeal to the following idea. If the derivative of z is symmetric, that is, d phi dz is the same plus and minus, then I claim phi itself must be antisymmetric. So I'll say, therefore, on the wing, phi at z equals 0 plus equals phi at z equals 0 minus. Oops, with a minus sign. That carried away there. With a minus sign. And the one simple way to think about it is just think of phi as being a plus a1z plus a2z squared, etc. And now if I differentiate this with respect to z, I get what? I get a1, well, I probably need one more, a3, 0 cubed plus. I get a1 plus 2a2z plus 3a3z squared plus whatever. If I want this to be the same for both z plus and z minus, then a1 needs to be 0, right? Oops. Got carried away here. Let me go back again. 2, yeah. Oh, okay, I'm okay. 3a3 z squared. A2 needs to be 0, right? And A4 needs to be 0. And A6 needs to be 0, right? Okay. But now if I go back to here, if A2 is 0 and A4 is 0, the only thing that are left here are the odd terms, and those are anti-symmetric when I change plus z to minus z. I have to think about this. Remember what the velocity potential is. If I differentiate it, I get physical quantity. So when I differentiate a constant, I get 0, obviously, and that doesn't really interact. So anyway, it's just a way to think about it. So now I know that this is true, right? Again, appealing to the fact that when I go to the trailing edge or leading edge, there must be continuity between what's happening on the wing and what's happening off the wing. Okay. Yes.
if it's true at the boundary of the trailing edge and the where the air meets the wing, why does it still need to be true off the, like, if it's still, if like GP Z is 0 at the boundary, what says it's still 0, you know, a meter downstream?
Oh, I'm not sure which question you're asking me. All I'm trying to appeal now, I'm trying to justify that statement. Are you concerned about this statement? This statement I claim is true on the wing. Yeah, for the case where this is true on the wing.
It's just the continuity between on the wing and off the wing.
But then that's the next statement. Then I'm saying this is true on the wing.
Yeah.
And now I'm saying if I go back down to the trailing edge or I go forward to the leading edge and I'm at that point, which is the interface between the wing and the fluid, then I claim this still must be true. Okay? But then I'm going to tell you that remember what I said about the off-wing boundary condition, namely that the pressure must be continuous, right? Okay, I'm going to use that fact plus this fact to prove that phi and the pressure are both 0 off the wing. That's where I'm headed. Am I helping you?
Yeah, go on.
Okay. So this is true, but now I also have Bernoulli to appeal to, right? Bernoulli says that minus rho infinity d phi dt plus u infinity d phi dx. Right? This is how the pressure is related to the velocity potential. But if this is true of the velocity potential, this also must be true of the pressure, right? Because differentiating the velocity potential with respect to t and x doesn't change the symmetry and anti-symmetry properties associated with the velocity potential. Therefore, I conclude that p at z equals 0 plus must be equal to minus p at z equals 0 minus. Right? It's true on the wing. I'm getting a lift now, right? I'm going to get a net pressure. In fact, what I'm showing is the pressure on the bottom and the pressure on the top in magnitude are the same. It's just they're opposite in sign. Okay. But so this is true on the wing. It's also happens to be true at the trailing edge, right? It also happens to be true at the leading edge, and that's the interface with the fluid. Therefore, by continuity, I say it must be true in the fluid in the plane z equals 0. But I know that p up and p down, p at z equals 0 plus and p equals 0 minus must be equal everywhere off the wing in the plane z equals 0. The only way that can be true, again, same argument as before, is that this is the perturbation pressure now. The perturbation pressure is 0 everywhere in the area off the wing. Okay. Now, does that help us? Yes, but the lifting problem is inherently more complicated. Why is that so? Because remember what I said. I said I need to integrate off the wing. Oops. Oh, thank you. Okay. I need to integrate in this area off the wing. So let's review where we are in the lifting case, the case I just discussed. On the wing, I know this. Okay. Off the wing, I know that. And I don't know this, because this, remember what this is. This is really d phi dz. Or you can think of, from the boundary condition, it's the fluid velocity off the wing, really, when I'm off the wing. So I need to be able to solve this equation, if you will, knowing partial information with respect to the integral and partial information with respect to what's outside. And the way you do that is you take this region and you divide it into little boxes. Assume that all of these things, phi bar and w bar, are constant within a small enough box. And then this integral equation becomes a system of linear algebraic equations, right? where some of the knowns are on the right hand side and some of them on the left hand side, and then I have to rearrange the boxes so that I can solve the problem. So let me spell out more particularly what I mean by that. Let's see, where are we now? 6, 7. So I've got phi bar of x, y, z has been set to 0, and omega is whatever it is. And this is equal to a double integral. I won't bother to write down the limits on the integral of w bar a and c eta. And then this thing that's an inverse, I'm just going to call it a function of x minus c, y minus eta. Also depends on frequency, and it's c eta. And now I'm going to introduce some notation. I'm going to say I'm going to talk about points in a box of dimensions delta c times delta eta. All right, these are just the dimensions of any little box. And therefore, I can say, to some approximation, phi bar at in the center of some box, I tells me is a box number. Z is set to 0, and of course I have omega. Is equal to a sum over all the boxes I, right, of w bar a, ci, eta I, that's the center of some other box, but with coordinates c and eta, times a of, oops, Susan, I need it. Sorry about that. I need to distinguish between eta and c and eta and x and y. So it's got to be a different subscript, j. The j and I are both box numbers. Different box numbers, but they're both box numbers. So I have xi minus cj, yi minus eta j, delta c, delta eta. Okay. Thank you. But I can write that in matrix notation. It's just all these phi bars, center of all these boxes, right, is a matrix A times all of these W bars. But again, the idea is that I don't know all the W bars initially, and I don't know all the phi bars. Okay? So I want to distinguish, when I write down this equation, I want to rearrange the boxes so that I distinguish between boxes on the wing and boxes off the wing, right? So phi bar, here's off the wing. And here, oops, sorry, are on the wing. And then over here, I want to do the same thing. These are the ones on the wing. And then these are the ones off the wing. Thank you. And then I have to divide this up in a similar fashion. Right? This is A. Now, over here, I know what? Off the wing, I know that the phi bars are 0. And over here, I know the W bars on the wing. These are known. But these are unknown. I don't know the W bars off the wing. On the other hand, I don't know the phi bars on the wing. Right? Well, what can I do? By dividing this up, I can initially solve the last several equations, the ones that correspond to off-wing bound conditions, for these W bars off the wing, right? In fact, let me do this. What's a good notation? Let's see if I use on and off. That's I need more than O's. Let's call it. What notation do you like? On. Well, no, that's going to be too complicated. I'm just going to do this, if you'll permit me to. And you'll have to remember that 1 corresponds to on the wing, and 2 is off. Okay? So now, do it this way so you can see it. I'm going to solve the last equations for this off the wing. What do I know? I know that 0, this is the last several equations. Darn, that's not working out. Well, let me write it again. It'd be easier to do that than... Look at the last several equations corresponding to off-wing conditions. What I know is that 0, that's V bar off the wing, is 0. Okay, is equal to A21 times W bar A on the wing plus A22 W bar A off the wing. By the way, this is going to be a square matrix. You'll be happy to know that. But this in general will not be square, but that's all right, doesn't matter. Because we're not going to do anything funny with it, like inverted. So, how do I solve for this off the wing? Well, I say this is equal to that, and then I invert this matrix and multiply that side, and I'm done. Aha. Now I know this everywhere, both on the wing and off the wing. And then I can just do is, I can take the rest of the equations and perform a matrix multiplication, and I'm done. Okay. You'll be pleased to know that there are companies that make a very good living providing you with software that does all that. Okay. And this is a little tricky because the Mach lines, if you look very close, these A functions are singular along the Mach lines, but they're weakly singular. That is, they go to infinity like 1 over the square root of the thing that's going to 0. So you have to be careful about how you construct the boxes and how you evaluate the coefficients in the A matrix. And that required someone doing a fair amount of hard work to figure that out. Also, remember in our discussion, we were saying that the pressure, the perturbation pressure, for this case is 0 off the wing. Oh, well, that's good. And we said there's continuity, and therefore you would expect the pressure to be 0, the perturbation pressure to be 0 right at the trailing edge, which is the interface between the pressure, between the wing and fluid off the wing, and that's what we like. There is a small problem. the pressure at the leading edge, according to this theory, goes to infinity if it's a subsonic leading edge. Even though we're in a supersonic flow, there is such a thing as a subsonic leading edge, meaning that if you look at the Mach number normal to the leading edge, not the free stream Mach number, but the Mach number normal to the leading edge, it can easily be subsonic. That component can be subsonic. When that happens, it turns out that the pressure at the leading edge goes to infinity. This is well known in subsonic flow, and it happens in supersonic flow too, depending on what the Mach number is. Okay. Now, if you watch closely, that violates all those conditions I was talking about. I was using the continuity argument to show that the pressure perturbation is zero off the wing, which is in fact the condition we use to work out these solutions. But then there can be a jump from zero to infinity as I go on to the leading edge. What's remarkable, well, first of all, it's a weak singularity. So if I take that pressure distribution that goes to infinity and I integrate it to get lift or moment or any generalized force multiplied by mode shape, I get a finite number. You'll be happy to know that. And what is true is you go into the wind tunnel or make measurements or you run an average oscilloscope, the pressure does not go to infinity then, right? But it does get really high. In fact, usually it gets so high that it's hard to measure the pressure near the leading edge in a wind tunnel experiment. So everything works out more or less, more or less. But there are singularities in this theory that would give a mathematician pause and gave a lot of aerodynamicists pause in the beginning. But now the theory has been used so long and so usefully that those of us who've been doing it for a while are accepting of these imperfections, if you will. But they're really there. So when you run the code and you try to and you plot the pressure distribution, you'll see these singularities appearing, or near singularities appearing. Of course, if you're doing boxes of finite dimension, you're never right at the leading edge, right? You're always at least a half a box length away from the leading edge, so you never really get there. In fact, you don't want to go there numerically because you'll get in trouble. Which tells you want the boxes to be small enough you get a good answer, but not too small that you get a problem with the singularity at the leading edge. Okay, how do we do? Oh, we have 10 minutes, so I'm going to relax now. I've done all the work I wanted to do today. Questions? We're going to think about it. We'll read the book. Now, next thing we're going to do is we're going to do subsonic flow, right? Moving right along. What are we going to do in subsonic flow? We took a Laplace transform with respect to x for supersonic flow, Fourier transform with respect to y. Can we still take a Laplace transform with respect to x in subsonic flow? You can have a 50-50 chance of being right. What? Yeah, why not? That's right. Why not?
Because you have information from the data.
Yeah, that's right. The flow is disturbed everywhere. So if you try to do something like this, you would first of all take a Fourier transform with respect to x now, and a Fourier transform with respect to y, which would be fine. And then you could get a formulation just like what I've discovered. When you did the inverse, you would discover the inverse in subsonic flow looks different from the inverse in supersonic flow, but you could do it. But there is a slight practical problem. The flow is disturbed everywhere in the plane z equals 0. Everywhere. I mean, right on out to infinity. So you're going to need a lot of boxes. In fact, if you watch closely in supersonic flow, when the Mach number went to 1, remember there's that beta factor? I'm at this point, and I'm in the plane z equals 0, and I have the Mach lines like this. The Mach number goes 1, the Mach lines become vertical and parallel to the y-axis. So the boxes go out to infinity, even in supersonic flow as the Mach number approaches 1. But then when you go subsonic, it's everywhere, right? So So the method I just described for supersonic flow has a real problem when the Mach number gets too close to 1. Right? So you'll see a lot of plots where people have calculated flutter boundaries, and they have a calculated point at 1.1 and another one at 0.9, and maybe 0.95, maybe 1.05, but not too often right at 1. Okay, but they pass a curve through it and hope they get a decent answer. So, but in subsonic flow, we're really in the soup. So we've got boxes everywhere. So what are we going to do? You have to come to the next class to find out. But I'll tell you basically what you do is you reverse what's known and unknown. Remember, in this formulation, this at least on the wing is the motion, right? And this is what we'd like to know on the wing. Well, you can reformulate this so that this is outside the integral and this is inside. In fact, you can do something else. You can use Bernoulli's equation. So this is outside, and what's inside is not phi, but pressure. And now the integral is the integral of an aerodynamic kernel function, or Green's function, times the pressure distribution, perturbation pressure. And formally, it's still the region is everywhere, except for the lifting problem, we know the perturbation pressure is what off the wing? It's 0. So when we put the pressure inside the integral only has to be over the wing. That's the good news. Well, the sobering news is the pressure is what we want to know, and now the pressure is inside the integral. So we have to invert the integral equation, if you will. We invert the convolution equation. And that turns out to be very subtle. And that was sort of the last thing people figured out how to do. And the first method I'll describe briefly, which is no longer used, but it was the obvious thing to do, and therefore it's probably worth mentioning. Since you may wonder why the heck we're doing what we are doing, since there's a more obvious way to do it. Well, it turns out the obvious way has some challenges. And so a new method was devised, not so many years ago, maybe 30, in relative time, maybe 30 years ago, which is the method that's buried in most of these codes that exist. And you'll be happy to know that, again, there are companies out there selling codes that do that for you using the new method. Okay, so read ahead if you're inclined to do that about subsonic flow, and you'll see that the formulation is similar. The details are somewhat more challenging. Anything else before we conclude for today? You are now expert aerodynamicists if you've understood most of what I said.
Did you say at some point that dpdz is equivalent to the flow velocity?
It is the flow velocity. It's the component of the flow velocity in the c direction. Okay, because the velocity potential is the potential from which we can derive the flow velocity components. So anytime I take a derivative of phi with respect to one spatial coordinate or another, I get the component of the flow velocity in that direction. Okay? Is that fair enough?
Yeah, I thought we were saying that was like the whole flow velocity. That didn't make sense.
No.
The whole, obviously, mostly being the x direction.
No. The whole flow velocity, if you ask. The whole velocity is u infinity plus, thank you, d phi dx. So this is a perturbation, right? That's the component in the x direction. The component in the y direction is this, and the component in the z direction is that. So if I want to know the total velocity, I square each of these and make the square root. That'd be the total magnitude of the flow velocity. Yeah. But in our linear theory, we're always assuming that these things are small compared to these things.
Yeah.
But not too small, because if we assume them too small, we'll throw them away altogether. We can't do that. But we retain the linear terms in these quantities and ignore the nonlinear terms. Okay, very good. We're moving right along. And I'm sure you'll all want the opportunity to